Hey, Mr. Landfesti.
Yes.
I was trying to put in the AP Physics website into Twidla and it didn't work. It won't upload the pictures.
Okay, and I guess that's all right. That you could just do a Twiddle and sketch. I just
Okay,
thought that would be easier. Sorry about that.
no, that's fine.
Okay, I'm going to go ahead and get started. It's probably going to be too much time to actually go around and have people share their whiteboards with people. Um, but maybe we can get consensus this way. Either answer, or you could just kind of say, when you were pulling this brick along the surface, so you started off pulling where there's slack in the string, and then you pulled it for a few seconds like this. What did the force versus time graph look like once it started moving? So I'm talking about in this region right here. What did it look like? Can you guys hear me?
Yeah, I can hear you.
Okay. It was straight. Straight meaning kind of horizontal, right? So it was a nice constant relationship. That was where we have the kinetic friction. What did it look like over here for the static friction? What kind of relationship was that? You can either say it or you can chat it in. What kind of what kind of slope, Jesse? What kind of slope did it have? Was it negative slope, positive slope? What kind of slope was it? Positive. Yeah, so here where we had the static friction, you had this positive slope. It might have been a little bit higher and then it dropped down once it starts moving. Okay, so that should have been what your graphs looked like when you were doing this. Okay, so what this is telling us then is the maximum static friction. So I'm going to say that this represents static friction. The maximum was greater than the kinetic friction. Now, I went around and saw yours, and yours didn't actually, well, a few, I guess, but most of them were actually just kind of going right up to it and it leveled off, it plateaued. But a few groups had it kind of humped up, and that's true that's usually the case. I'm not sure why it was. Maybe it's because it's metal really slick or something. But it's usually greater than the kinetic friction. It's not equal to, it's greater than. So any questions about that? Hopefully that's what you guys saw. So now I want to kind of go on then a little bit. I want to look at what you were doing then was you were doing this experiment 6 times to find different kinetic frictions, and you were plotting that kinetic friction versus the normal force. And so I kind of wanted to get some kind of consensus, and I think it would just simply be faster if you kind of texted me or you just simply said what kind of relationship you got. Okay? I don't need to know the mathematical relationship. I just need to know what kind of relationship it looked like on your graph. We have one person that's responding. Okay, got a couple. Okay, it looks like you guys are saying, okay, positive direct. Okay, so kind of like this. It looks to me like most people are saying that. Okay. Anybody have something different than that? We can look at their graph. Okay. So I think this is going to go faster this way if we do it this way. I'm sorry, it's not exactly like being in class where we can go around and look at everybody's whiteboard, but I'm hoping that if you got something different, you'll say something so we can check out what you got. We can kind of troubleshoot. Okay, so what this means is that the kinetic friction is going to be directly related to the normal force. So you probably had different numbers here. So some number times the okay. I'm not going to put the number because more than likely it was different for other people. But let's talk about the units. What were the units? You can either say or you could type it in. What were the units of the slope? Think about what slope is. Yeah, rise over run. There you go. Yep. Okay, got a few people texting in. That's good. So it's newtons over newtons. So that cancels, right? So actually there are no, this is one of the few times where we don't have any units here. It's just simply a unitless ratio. They cancel, no units. More than likely your numbers are pretty close because we were all doing paper on the metal, but some of the metal had some tape on it, and so it's stickier and stuff. So we're not going to compare numbers and average or anything, okay? Because they're a little bit different. This number right here, that's kind of a stickiness factor. I'm not sure if that's a real word, probably not. It's kind of how sticky the surface was, okay? So that's the next thing I want to look at. That's called the coefficient of friction. That stickiness factor is called the coefficient of friction. Before we look at this, there's going to be two different stickinesses of friction. There's going to be a kinetic stickiness of friction, and there's going to be a static. There's going to be a static coefficient. Which one do you think is going to be more, the kinetic sliding, or do you think the static is going to be more?
He's currently at work right now.
You could text it in, or you could say, right, the static. Okay, so let's look down here at these coefficients. These are static. Okay, remember how we found there are two factors that affect friction, the support force and the type of surface. Well, these coefficients of friction are related to the type of surface it's on, so surface type. And you'll notice that every different kind of surface is going to have a different stickiness factor. So steel on steel, the coefficient of stickiness is 0.74 for static, and for kinetic it's 0.57. So indeed, the static's more than the kinetic. If you come down here, glass on glass, it's 0.94, and then kinetic is 0.4. And then for really slippery things, Teflon on Teflon, static is 0.04, kinetic is 0.04. And actually, something that's actually more slippery than that is your joints. And that's some place where you want to have very little friction, and static friction is 0.01, and kinetic friction is 0.003. What do you notice that these numbers always vary between? What two numbers do they always vary between? There you go, between 0 and 1, between 1 and 0. Okay, that's because it's a ratio. Okay, so let's say you have a lot of friction. What do you think the mu, actually that's called mu, if you're wondering what is that funny looking symbol, it's mu. It's kind of like a sick kitty cat sound. It's mu, mu. So that's mu-s and mu-k. But anyway, let's say we have something that's very high in friction. What do you think the stickiness factor is? The mu, what do you think that would be close to if there's a lot of friction? There you go. It's going to be close to 1. And if it's very slippery, there's hardly any friction whatsoever, it would be close to what? 0. There you go. So any questions? So here is our consensus model. The only thing we need to add to this is a generic value, which I'm going to call mu k. And the k again is for kinetic friction. That's our consensus model. Okay. Any questions? Okay, there are some limitations to this model. If you're thinking, well, that doesn't make sense. I'm really in racing, and I know that friction connect would be more than that. You need to understand that we're only looking at 2 types of friction here, and that's static friction and kinetic friction. Some people actually mentioned rolling friction. That's a different type of friction. But actually, if you're into racing, there's a totally different type of friction that's actually related to adhesiveness. And by the way, I'm going to give you this table tomorrow, well, next time we see each other, and I'm going to give you this information here about limitations of our model. It's not that you need to know this limitations. I just thought if you're curious, if you're wondering, well, I'm really into racing and I know it can be more than that, and they rate tires based upon how well they stick to the pavement. You're right, there is a different type of friction. Okay. All right, I want to skip on down. On the back side of your lab, it asks you to figure out what angle that your brick starts sliding at constant speed. And I want to analyze that. Let's say that we have the brick that has a mass of m, and the angle here is theta. Okay, so what I want to do, what's the very first thing I have to do after I have a picture and I want to solve a problem dealing with dynamics? What's the first thing I have to, yes, I have to draw a free body diagram. So what's an easy force that we know is always going to be here on Earth? Weight. Okay, so I'm going to go ahead and draw my weight vector. Hey, that's not bad. That's pretty good. There's my weight vector. And what's another one that's occurring whenever it's being supported by something? What's another force? Yep, the normal force. Now be careful, we call it normal because it's perpendicular to the surface. So the surface kind of goes like this. Oh, by the way, I see a lot of people rotating your free body diagrams. You cannot do that. You need to draw the free body first, and then if you want to rotate the paper it's on, that's good. Go ahead and do that. But do not rotate your free body diagram, because in the AP test, everybody knows the weight's straight down toward the center of the Earth. If you draw it at some other angle, you automatically miss that. Okay. Okay. Now the normal force is going to be perpendicular to that surface. So hopefully I did a okay job there. Okay. Notice that the length of this Fn, or excuse me, this normal force should be about the same as if I were to drop a perpendicular to my dotted line here. Okay. All right. If it's going at constant speed, there must be another force here. What other force am I missing? Friction. Which way would that be? Would it be down the ramp or up the ramp? Up the ramp. Okay. So if it's going at constant speed, I have to be careful how long I draw it. I need to draw it so it's about the same length as the other side of my triangle that I just drew. Hopefully that's close. If it's moving, what kind of friction would that be? Is it static friction or is it kinetic friction? It's going to be one of those two. Which one is it if it's moving? Haley, which one would it be? Okay, yeah, kinetic friction. There you go. So kinetic friction. Now keep in mind that I need to rotate this piece of paper So I just drew my free body, and now I'm going to rotate the paper. So hopefully you got a piece of paper there, you're sketching by hand, or you got your lab there, you're sketching by hand. Now rotate the paper along the y-axis, or excuse me, along the normal. That's the y-axis, and the other one is the x-axis. Okay. So now this angle theta here for my ramp, that's going to be the same as this angle here, theta. That's kind of the hardest thing for kids to, for students to see. Anybody need me to explain the angle theta? Anybody need me to go over that? Okay, it looks like we're okay with that. All right, so now what I want to do, after I have my free body, what's the next thing I do in my procedure? Yeah, I have to write some equations, right? Okay, so I need to write some equations, and I'm going to start off with the y direction, okay? In the y direction, let's see, I don't like blue anymore. I like the black. The normal force must be equal to what? What is the normal force going to be equal to? Yeah, the weight in the y direction, W in the y direction. Any question how I knew that? It's this side of the triangle right here. This part, that has to be the same length. Okay, what trig function would help me figure out how long that is? What trig function? Okay. Do you see, I'm getting cosine and I'm getting sine. Yeah, it's cosine, right? Okay. Everybody, yeah, there you go. So it's going to be the mass times g to figure out the weight, but then I would multiply by the cosine of theta. Okay, so we're okay with that? Okay, now I want to go ahead and figure out another equation here. Let me get back to, that's all right. Now let's look at kinetic friction. Keep in mind this thing's going at constant speed. Yes, I do know my mathematical model up here is Fk is equal to mu k times normal, but I'm going to skip that, and I just want to look at my free body diagram. What's Fk going to be equal to? Can everybody see it's going to be equal to Wx? I hope so. And what trig function would give me the Wx? That's this side of the triangle, the sine, right? So this is going to be equal to mg over sine of the angle.
Mr. Lundquist, do you have a question?
Yes, question. Yeah, James.
All right, so we went over this at my old school, and they called it the parallel and perpendicular force. Doesn't matter.
Yeah. No, that's fine. You could do that. So yeah, the parallel to the ramp would be the frictional force and the weight force that's parallel to the ramp, and so that'd be mg sine theta. And then perpendicular ramp, that would be the mg cosine theta. Yeah, that's fine too.
All right, cool.
Okay, then I'm going to go a little bit further now. I want to use our mathematical model we just found, and that was that the friction is equal to, the kinetic friction is equal to the coefficient of friction, UK, times the normal. Okay, we just found out what Fk is. It's mg times the sine of the angle. And we have mu k on the other side times the normal. And the normal is going to be mg times the cosine of the angle. Okay, I want to solve this from UK. So that means I'm going to have to divide by mg cosine of the angle. What happens to the m and the g? Okay, cancels, right? And then, I'm not sure if you guys know this, it depends upon where you guys are in your trig. Does anybody know what sine of theta divided by cosine of theta is? Okay, it looks like a lot of you guys do. It's tangent of theta. Not sure if everybody knows that or not, but sine of theta divided by cosine of theta is tangent of theta. So what that means is that if you got something moving down a ramp at constant speed, if you know the angle theta, whatever that angle is, 10 degrees, 20 degrees, whatever it is, if you take the tangent of that angle, that's going to give you coefficient of friction. And so what I want you to do right now is, remember how in the lab that you measured what your angle was, whether it was 10 degrees, 12 degrees, whatever? Get out your calculator, make sure it's in degree mode, and take the tangent of that angle. So I'll give you like 30 seconds to a minute to do that. Okay, that should be enough time. Now what I want you to do is compare that number to your slope when you plotted FK versus the normal. So compare the tangent of that angle, that number, whatever that was, to what your slope is. How do they compare? Are they close? Pretty close, right? That's because you pulled it along the metal ramp, and then you use the same metal ramp to slide it down. So let's say somebody made a mistake. Well, let's say somebody did the lab a little bit differently. Let's say somebody was pulling the brick along the lab table, not the metal ramp. And then they took the brick and put it on the metal ramp, and they tilted the ramp. Would the angle, tangent of that angle from the metal ramp, would that give you the same value as their slope if they did it that way? Let me say it again because I'm not sure. Maybe I confused you guys. So let's say a group, instead of doing it the way I explained, they actually went into the lab and pulled it along the lab table instead of the metal ramp. And they plotted FK versus normal, and they found their slope. And then they put the brick on the metal ramp, and they slid it down the ramp. Would the tangent of the angle from the ramp be the same as their slope? I'm getting a few of you saying no. Does that make sense? It wouldn't be the same, right? Because it's different coefficient of friction on the lab table and on the metal ramp. Okay. All right, I'm going to go ahead and go on. Does anybody have any questions at this point? So you should be able to finish up the lab response now. Any questions? Okay, I'm not hearing any questions. So, oh, one more thing probably with the lab. What were some numerical constants in your lab? In other words, what was something that was kept constant? Now, of course, the paper, that was kept constant, and the fact that it was on the metal lab table, or on the metal ramp, that's constant. But there wasn't a number associated with that. Anything you could think of was constant. Well, think about what affects, there you go. I see one person saying gravity. That was a numerical constant. Thanks, Brian. So that was a numerical constant, right? Would we expect the friction to be different, or would we expect the friction to be the same on, let's say, Mars compared to here? Do you think the friction would be the same? No, right? Because that's going to affect the normal force. Does that make sense? Let's see, anything else that was constant? Well, we know that surface type affects it, but we didn't really know the number there. So there's not really a number. And we know the support force, which is related to the weight, affects it. And the weight's related to the gravitational field. So I think there's only one constant here. Any questions? I suppose somebody might say maybe the angle, but I think we all agreed that the angle is going to be 0 degrees, right? So I don't really think that was a constant. All right, I'm going to move on then. You should be ready to turn in that lab then on Friday. I want to go over worksheet 4 because I didn't grade, for worksheet 4, I did not grade the ramp problems. I did look at the free body diagram. That was the only thing I looked at. Like, so for number 4 and number 5, I looked at your free body. That's it, because I thought that's fair. You should be able to draw a free body. But we hadn't whiteboarded any of the problems like that, well, at least not for a long time. So I didn't really grade those. So what I thought I would do is, after we do number 5 and number 9, I thought perhaps if you would like to resubmit just the ramp problems on worksheet 4, you can. If you're pretty confident you got them right, then you don't have to do anything. Any questions on what I'm talking about there? Okay, so if you feel like you did the ramp problems all right, and you're just going to go with what you turned in, that's fine. I haven't graded those yet. I graded the other ones that you should have been able to do. Don't worry about this. In fact, you could probably sign off if you feel like you did them right. Okay, I'm going to go ahead and go and look at number 5. Number 5, what it says is we're assuming that now it has friction. So I want to go ahead and draw a free body. So what are some forces here? Always start off with an easy force. There's a weight force. Okay, so there's a weight force straight down. Okay, there's this tension force, right? So I'm going to go ahead and draw that on there. We have a tension force. That's an easy one because they show it to me, Ft. There's a normal force. Good. So there's a normal force that's kind of perpendicular to Ft. It's perpendicular to the ramp. And it's going at a constant speed. I think it's going at constant speed anyway. Or no, it's not going at constant speed. It's accelerating. But anyway, we're supposed to find the frictional force. So there's probably another force here. We're pulling up the ramp, so which direction is the frictional force? What do you mean exactly, Dakota, about left? How about down the ramp? Is that, other people are saying down. How about down the ramp? Is that okay? Dakota, is that all right? Okay, down the ramp. All right, so there's my frictional force, Fk. How am I doing on time here? Okay, so Fk. Again, you don't want to rotate your free body diagram. You can kind of dot in your x and y axis if you want to. So there's my y-axis going through the normal. Here's my x-axis. And then, if you want to, you can rotate your paper. Okay. So notice that the angle over here is 35 degrees. What that means is that, I'm going to do a different color. That means that this angle right here is 35 degrees. All right, so the first question says, what is the x component of the force of gravity? The x component. So that would be, I haven't drawn it in here, but that's kind of this side right here. What trig function is going to help me find that? Okay, I'm seeing one person say, what trig function is going to help me find this side over here of my triangle? Okay, a couple people. Yeah, it's going to be the sine, right? So I'm trying to figure out what Wx is. So Wx is going to be, I feel like I'm lecturing to you guys. I don't really like lecturing. I hope you guys, if you have questions, please stop me. Okay, so this is going to be the mass times gravity, because that's what weight is. And then the x component, you guys, is found by using sine. And the angle here is 35 degrees. Any questions how I figured that out? Okay. All right, so that's going to be equal to 150 newtons times the sine of 35. And I think that's approximately, if you use your calculator, hopefully you guys are checking me. Uh-oh, did I do this one? I think I did. Anybody do this? What do you get when you do that? 150 times the sine of 35. Oh, good. Somebody's got my back. So 86 newtons. Okay, so now I want to figure out the acceleration. Question for you. Look at my picture. Not so much on the free body, but look at the picture. Which way do you think this thing is accelerating? Which way is it accelerating? Up the ramp, right? So kind of like this. I'm going to call this A. That's not a force, that's the acceleration. It's that way. So I'm getting ready to write a net force equation. So F net is equal to, help me out here, no numbers. F net is equal to what? Well, that's true. F net's MA, you're right. But look at your free body. I'll give you a hint. It's going to be like a this force minus that force kind of thing. Okay, so I see a lot of people saying the tension force. So Ft, because that's in the same direction as my acceleration here, Ft minus, and I see some people are putting the frictional force. You're right. The frictional force is opposing it. But a lot of people are missing one other one. There's a few people getting it. Can you see that there's also an x component of the weight? So the weight's not helping us move up. So it's opposing us, so Wx. So this is going to be, Ft is 150 newtons minus the frictional force, and the frictional force is given to us as 25. Minus the weight, which is, or weight in the x direction, which is 86. Okay, don't forget this is MA, so this is going to be 15 times A. So why don't you guys take a moment here and calculate A and see what you get. Okay, so everybody can get out your calculators. I got 2 people typing in. Go ahead and type it in and see what you get. We're getting close to being done, guys. Okay, looks like I got quite a few people anyway. So 2.6 meters per second each second. Okay. I did have another question here. This isn't really on your worksheet, but I thought it might be interesting to do. Okay, so to find the coefficient of friction, that would be Fk, using the new mathematical model we have, is equal to mu k, that's that stickiness factor, times the normal. Well, we know what Fk, or yeah, the friction, Fk, that's 25 newtons. 25 equals, but the thing we don't know is the normal force. So looking back at my free body diagram here, could I write an equation for this? What is the normal force equal to? What's N equal to? Looking at my free, yeah, can you see that? It's equal to Wy. It's equal to Wy. Any questions? Okay. And that's going to be equal to the mass times gravity, so it's going to be 150. Gravitational field strength, I should say. Mass times gravitational field strength. Times, what trig function will give me the y component? Cosine, right, cosine of 35. Any questions how I figured that out? Okay, I don't want to figure out what n is. I think you guys can do that. But what I want to do is I want to figure out what mu k is. Okay, so could you guys go ahead and solve for n and then solve for mu k, and then once you get an answer, can you go ahead and chat it up there or say it out loud so we know? Okay, it looks like most people are responding and they're getting 0.204 about. Any questions how we got that? We're all good? Okay, so we have one more and then this is it. This is number 9 from that worksheet. Okay. For this one, I went ahead and drew the free body because I know some people are having a hard time with the free bodies. Okay, so I went ahead and drew the free body. It says, given the free body, which way is the system moving? Okay, so I don't want you to type anything yet. I want people to think first. Okay, and I would like you to write it down on paper. Don't type it in. Don't chat it yet. Don't say anything. Just write it down. Which way you think it is. Just think about it. Okay, can you go ahead now and chat it in? Which way do you think it's moving? Okay, that should be enough time. Can you go ahead and chat it in? Okay, I'm getting different. I'm getting down the ramp, question mark down. A lot of people aren't sure. They don't want to guess. Down. Not getting a whole lot of people, so I'm thinking a lot of people are not really sure here because it doesn't say, right? Okay, I have a few people who are saying down. So can you guys, the people who said down, can you give me a reason why you think down? Or not? Maybe you guys can't. Okay, well, let me ask you a question then. Okay, so we're getting a numerical reason. I don't really want a numerical reason. I want a conceptual reason. Ben says, okay. Ben's reason is also kind of a numerical. Let's go to Logan's reason there. Oh, and Adriana's reason. Let's go with both of theirs. That's a conceptual reason, and those are good conceptual reasons. So I want to stay away from the math, and I want to stick with conceptual. Remember how friction always opposes, well, kinetic friction opposes the motion. So it's not going to help this thing move faster. So Matt, let's just think for a second that it's moving up the ramp. That means that friction is helping it move up the ramp. That's not true. Friction doesn't help. So friction is opposing the motion. So if friction's up the ramp, then it must be moving down the ramp. So yeah, it is moving down the ramp. The way we know is because the friction is in the opposite direction. Okay. So the reason, or it's down. It is down. Down ramp. How am I doing on time? Okay, a little bit more. Okay. The next question is, what's the mass of the object? Okay. Go ahead and chat it in. What's the mass of the object? Okay, get a couple answers there. Good. Make sure you're showing your work when you're doing your worksheet, because again, that's what they're going to look at on the AP test. The weight is equal to mg, and since we know the weight is 130, that's going to be equal to the mass times 10. And so, yeah, you're absolutely right. It is 13 kilograms. Nice. Okay, what's the normal force? Well, if I want to find the normal force, that's going to be equal to what, I guess? I'm not asking you a mathematical answer. What's it going to be equal to? What force or component of force? I'm getting two different answers, Wx, Wy. Most people are saying Wy. Okay, all right, Wy, that's right. So if you're confused about that, what we're talking about here is if we draw in something like this, as James pointed out earlier, maybe I shouldn't say Wy, maybe I should say it's going to be the component of the weight that's perpendicular to the ramp. Okay? In other words, it's going to be this side of the triangle right over here, this side right here of the weight. Okay? And this angle here of 28 degrees is the same as this angle here. That's 28 degrees. So now you can go ahead and solve this problem. This is going to be equal to the weight, which is 130, times what trig function is going to give me the y component? Yeah, cosine. Good. Cosine of the angle, which is 28. And I'll let you guys solve that later on. Okay, then finally it says, what's the magnitude of the acceleration? Looking at this, if it's accelerating, we don't really know if it's accelerating, but if it is accelerating, which way do you think it's accelerating? Yeah, down the ramp, parallel to the ramp, down, yeah. Let's say the acceleration's that way. I need to write a net force equation. Now it's true, I know F net's equal to ma, but that's not really what I'm talking about. When I say write a net force equation, I'm talking about looking at your free body and writing a net force equation from the free body. So which of these forces over here, normal, Fk, W, which one's causing it to accelerate down the ramp? W. Is all of W causing it? Just the X component, right? So I'm going to write Wx. Is there any forces that's opposing the Wx? The friction, right? So that's going to be Fk. Okay. Now I know what Fk is. That's the 61. What trig function is going to help me figure out what Wx is? Sine. So that's going to be 130 minus, I only have 3 minutes left, minus, oops, 130 sine of 28 minus the friction, which is 61. Don't forget, now this is where we plug in what F net is. It's MA, which is, the mass you said was 13. So it's going to be 13A, and then you can solve for A. Since I'm out of time here, any questions? I didn't actually solve this. You need to solve it, but I think you're okay. Any questions before I let you go? I'm sorry it was kind of rushed. I'm sorry that it was kind of a lecture, but I hope it worked for you. All right. Well, thank you for attending. See you guys tomorrow, hopefully. Bye.